Hey everyone, welcome back, and today let's solve Leetcode problem 1765 titled Map of Highest Peak. So I am recording this video pretty late at night. I don't want to disturb my neighbors or anything like that, so I'll try to be as quiet and quick in today's video as possible. So we're given an integer matrix is water of size m by n that represents a map of land and water cells. So if his water, that matrix at index ij is equal to 0, well then that cell ij is a land cell. However, if the cell is equal to 1, we know that that specific cell ij is a water cell. And we must assign each cell a height in a way that follows these rules. The height of each cell must be non-negative, and if the cell is a water cell, its height must be exactly 0. And additionally, any two adjacent cells must have an absolute height difference of at most 1, meaning it can be either 0 or it can be 1. And a cell is adjacent to another cell if the former is directly northeast, south, or west of the latter, meaning their sides are touching or therefore directionally adjacent. We need to find an assignment of heights such that the maximum height in the matrix is maximized. And we need to return an integer matrix height of size m by n, where height at ij is the cell ij's height. And if there are multiple solutions, we have the option to return any one of them. So to better put this problem into context, let's go ahead and look at example 1 here. We have a 2 by 2 matrix as our is water input. It's 1, 0, 2, 1, right? And basically the 0 means that it is actually a water cell, right? So effectively, it says our output is going to be 1, 0 and 2, 1 because the image is going to show the assigned heights of each cell. Right, the blue cell that's highlighted in blue is the water cell, and all of these green cells would be the land cells. And notice how we're trying to maximize, as you can see here, the maximum height in the matrix, right, rather. And so 2 would be the maximum solution for that, and so we'd return this arrangement. In example 2, we have our input matrix to be 3 by 3. In this case, we have 2 water cells, and we have 1, 1, 1, 2, 1, 2, 2. In this case, notice how every single 4 directionally adjacent cell has a maximum, or rather has an absolute difference of at most 1 or simply just 0. And applying those rules to this problem constraint for this input, we see that the maximum cell of any cell value is going to be maximized to 2. We can't get higher than 2, and so this is one of the best solutions, and so we simply return this arrangement. A height of 2 is again the maximum possible height of any assignment or arrangement that we actually put this matrix in, right? And any height assignment that has a maximum height of 2 would still be accepted as long as it meets these rules that were given here, right? So basically, for the problem constraints here, we see that m and n are the number of rows and columns of the input matrix is water, and they're both within 1000, where every cell in the input is either going to be 0 or 1, basically either going to be water or land, always valid, and there is at least one water cell. So we're given that as always it's going to be a valid input. So with that problem statement, constraints, and examples out of the way, I will give you guys a few seconds. You're going to just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what is this problem really asking here? Well, basically, this problem can really be solved basically combining the breadth for search algorithm, also known as BFS, and also how the distances actually propagate outward. And to better put that into context, let's look at some key observations that we can really make here to help us lead to the most efficient solution to solve this problem. Well, the first observation is that effectively water cells are going to act as these sources of height propagation since they're fixed always at a height 0. That's constant. And so from there on, we simply assign the heights to adjacent cells based on their specific distance from the water, right? And for the second observation that's very important here, basically, this problem is effectively completely about the multi-source BFS, right? Multi-source BFS is simply a variant of the BFS algorithm, and the reason why it's about this algorithm, or variant I should say, is because we're actually simultaneously starting our height calculations from all of the water cells and simply really just expanding outward in each BFS level. right? So effectively, basically for a high-level rundown of the algorithm and solution structure, we're first of all going to use a queue to actually perform this BFS, a very common data structure for BFS and even DFS algorithms. Basically, we're going to begin from all of the water cells in the grid, and then, of course, expand outward from there. And effectively, each water cell would, of course, be initialized to a height of 0. And again, to kind of reiterate, we're simply going to propagate the height's values to its adjacent land cells and increase the height by 1 for every single step outward that we actually make. And to avoid revisiting any cells, we're also going to maintain a visited set, also for constant lookup time, or just directly update the grid with heights as we actually go. So for the data structures, again, to kind of reiterate, we're going to be using a queue to actually process the cells for that BFS order. We're also going to be using a 2D grid to actually store those specific heights for every cell in the input. And finally, of course, the direction vectors to actually explore the neighbors of a cell, which would basically mean the 4 directions that we can go in: up, down, left, all right, so with that high-level solution out of the way, let's go ahead and dive straight into the code here. So what I usually like to do for graph/matrix problems is actually store the number of rows and columns, basically the dimensions of the input, in 2 integer variables that I like to literally call rows and columns. And this is going to be simply the length of isWater and the length of isWater at index 0, right? This is kind of a neat way to get the number of rows and columns respectively in a matrix here. Basically, it's the number of rows and the number of columns, which basically always start at the 0th index of a matrix. Simply going to help us iterate through the grid and actually check for our boundaries. Okay, well now let's actually initialize our result data structure, and the way I'm going to initialize this is basically be -1 for all of the values or cells times a column in the range, so I'll use an underscore as my iterator here for this for loop here, of the number of rows. It's literally going to have the same dimensions as the input, because of course that is our result. It's basically the possible arrangement that we can actually make where all of the cells are set to -1. It's simply going to store the heights for the result, and setting the cells to -1 will all initially mark them as unvisited cells, because of course they're unvisited if we haven't visited them yet and iterated over the input. Okay, well, now that we're done with that, and now let's actually initialize our main data structure here. It's literally just going to be the queue is what I'm going to call it, and it's going to be equal to a DQ here. And what a DQ really is, it's basically a double-ended queue, and basically it allows for constant or big O of 1 time popping and appending from both sides, right? This data structure, this double-ended queue, or queue if you will, it's going to be actually used to perform that BFS algorithm. It's simply going to store these cells that we actually need to process, starting of course with all of the water cells. Okay, well now let's actually kind of introduce that operation. So first of all, let's actually iterate through the input matrix and actually build up our result and our queue in that nested loop here. So the way you can do that in Python is basically for R, is what I'll call it actually, in the range of the number of rows we have for our outer loop, and the inner loop is going to go for the columns, right? So for C, basically standing for columns, in the range of the number of columns we have nested loops to go over all the possible cells in this 2D input matrix. If the current cell, I should say, so isWater at RC, if it's actually equal to a 1, then we know we can set result at RC immediately to simply be a 0. And once we do that, we want to then append it, so q.append the current coordinate r comma c of length 2. It's simply going to be a tuple, right? What does isWater at RC really check? Well, it checks, is it a water cell? Because we know all the water cells are always going to have a height of 0, because the problem literally tells us. Again, we're iterating over every single cell using these nested loops here of our input matrix isWater, and if the current cell is a water, we're going to do 2 operations. First of all, we're going to set its height in the result at that specific cell to be 0, because that's exactly how our problem works, and we also have to add that cell's coordinates to the BFS queue, because of course we want to process and expand outward from all of the water cells, which marks the water cells as the starting points for that BFS algorithm that we initially store in the queue and build it up incrementally from there at each level of the BFS traversal. Okay, well once we actually process all the water cells and add their corresponding cell indices and update their results heights accordingly, now let's actually initialize our directions array. It's going to be the 4 cardinal directions, basically left, right, up, or down, that we can actually process through from each cell, right? So I'm going to initialize it as 4 different tuples of length 2 each. we're going to have 0, 1 as our initial direction. We're also going to have 1, 0 for our second direction. Then we're going to have 0, -1, and you guessed it, -1, or 0, 1. Or sorry, -1, 0, sorry. Right? These are literally just the 4 different directions that we can go. It's a list of direction vectors, rather, to explore the 4 possible neighbors of every single cell during that BFS traversal. Okay, great. Now, let's actually start the main while loop here while we actually have nodes to process in the BFS traversal as a whole. So while the queue is non-null, so while we do actually have nodes in the queue, we'll get R and C, the current cell, to basically be the leftmost value in the queue. So q.pop_left, popping it off from the queue and unpacking it and actually getting those specific cell indices and storing them in the R and C variables for this specific iteration. So to kind of reiterate, we're simply continuing along this while loop here while there actually are cells in the queue to actually process. So while the queue is non-null, and we're removing and processing the first cell in the queue stored in the R and C cell indices, right? That's literally the current cell that we are working on in this iteration. So now let's actually go through the directions, or the 4 neighbors of the current cell. So for every single direction, so DR and DC is what I'll call them for row and column in the directions array, we're going to get the new row and the new column, so I'm just going to call them NR and NC, to be R plus DR and C plus DC, right? Literally getting those coordinate or cell offsets here to move on to those 4 neighbors. For the current cell RC, we're looping through its 4 neighbors using those direction vectors and calculating the coordinates of those specific neighboring cells in each of the iterations of this for loop here, right? So now let's actually have that lengthy boundary check to see, well, is the actual for loop, or current new cell, is it actually a water cell, or rather unvisited, and is it actually in bounds? So the way we can check if it's in bounds is if it's actually within 0 and the number of rows we have, and, sorry, yeah, that works. The new column, sorry, is at least 0, so non-negative, because of course we can have negative indices in this case here for NC, and it's at most, or it's at most columns -1, and if the result at this specific cell, NR and C, if this remained unchanged, meaning it was equal to -1 as we actually initialize it, then we know we can increment or update its specific value, so NR and C, sorry about that guys, struggling to type here, to now be its current value, so result at RC, the original cell, +1, right? Literally just adding 1 to maximize our max value, because we're given that any 2 adjacent cells must have an absolute height difference of at most 1. And think about it, to maximize the maximum height, we want to keep adding 1, so we can have the largest possible value as our maximum result res, right? And effectively, once we actually do that, we'll now also actually append to the queue this current neighbor for actual future iterations, for future processing levels of the BFS traversal. So q.append the new coordinates NR and C, because we want to process them and use them in future iterations to explore their neighbors, right? So to kind of reiterate on a high level, what we're really doing here is basically, first of all, we're checking if the neighbor NR and C is actually within grid boundaries, and if it actually hasn't been visited yet, meaning its height is still initialized to -1 as we actually started it off with. Then if all of those cases are true, well, then we can assign the neighbor to a height that is exactly 1 greater than the current cell's height to maximize the maximum cell as our result. And effectively, we're going to add that specific neighbor for the current iteration to the queue for future processing. Then explores its neighbors, and so on and so forth. And effectively, once this while loop is actually done executing, we would have processed all the nodes in the queue, and we can safely return the result, whatever that would be, as a possible arrangement, basically, again, that 2D integer of the input, right? So after the BFS actually completes, this result grid as such is going to be 2D, is going to contain the final heights for all of the cells as our output. So unless I made any syntax errors here, this should be accepted and there should be a valid solution. And as you can see, this is really just about as efficient as you can really get it to be. So for a quick high-level rundown of how our code actually works as a whole, effectively to kind of reiterate, we're using a multi-source BFS, actually starting from all the water cells in our queue, and all of the water cells are actually initialized to a height of 0, and the heights actually propagate outward to all of the corresponding land cells, maximizing our maximum height by adding 1 for every single neighbor cell, because we know that adjacent cells in four directions directionally adjacent can only have at most a difference of 1, or rather an absolute difference of 1. And this BFS ensures that the height difference between the neighboring cells is always going to be at most 1. So for these runtime complexity here, this is actually going to be a big O of m times n solution. M and n are the number of rows and columns in the grid respectively. The reason why is because, think about it, we really only are visiting each cell exactly once during our BFS traversal. And for the memory or space complexity, it's also going to be big O of m times n, because we are actually using auxiliary memory, these extra data structures for the queue and the result as well, which is our bottleneck. And so we are going to have a simplified big O of m times n memory or space complexity as well. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.